Okay, so now we're ready to get started on Module 5. Module 5 is equilibrium of rigid bodies. So we have already talked about equilibrium, but that was in terms of equilibrium of like a point, a concurrent point system, or current force system that shares a common point. Now what we're going to do is we're going to be applying equilibrium to items that aren't necessarily concurrent force systems. They're going to be those parallel or non-parallel force systems that we were working with or started to work with in Module 4, but we're going to be taking it a step further. So if we look here at the learning plan, you're going to notice that we're going to go back into our ebook and we're going to reference chapter 4 in our McGraw ebook, okay? The sections that we're going to be covering are the first sections here, 4.1a, b, and c. And then you're going to notice that we do have some guided notes here that we're going to be working from again. So in the classroom, I have these printed. For those who are here, you can just fill in as you go along. For those who are virtual, make sure that you do print these off or duplicate them in some way, because this is what you're going to be handing in for the practice problems, this handout, okay? The handout includes all of the practice problems that we see listed here. So we're going to be doing some work and looking at all different types of problems here that'll prepare you then for your application problems. Underneath our learning plan, you're going to notice we have our session recordings. I do have the session recordings out there from last year, so you can always go in and reference those, and they're labeled there for you to look at if you so choose. Then you're going to notice here, this is going to be the assignment for the practice problems to hand in. So once we get through our guided notes, do all of those samples and example problems, then you'll be ready to hand those in. And then your application problems are then going to also come out of the Chapter 4 McGraw-Hill ebook, okay? It's not meant to confuse anybody. Chapter 4 was in Module 4, but Chapter 4 was a handout from a different resource. We're in Module 5 now. I know this is Chapter 4 again, but this is out of our ebook. So just pay close attention to whether you're in and working in Module 4 or Module 5, because we're referencing two different Chapter 4s in each one of these, okay? So those are there. So application problems we won't really worry about too much until we get through some things here already. Now, what I'm going to do is I'm going to go underneath my camera here. I do have the guided notes already printed out, and we're going to be starting on page 1. Now, I also have the physical book, the loose leaf version of the physical book for the McGraw-Hill. So I'll kind of be going back and forth if there's any illustrations or problems that we're going to be referencing. It'll be coming out of here, which again is the ebook that is provided in the Canvas shell for for technical statics. Okay, so starting at the top here, and this starts on page 157 in that ebook. They're talking about the concept of equilibrium, and we've already talked about equilibrium, okay? So when forces and a body are in, and the word here is going to be equilibrium, all the forces and the moments are equal to 0. When we talked about equilibrium, when we looked at equilibrium in Module 3, we weren't discussing moments at that time. Everything had a shared point, and they shared that common point. And so we only worried about summing forces in the X and summing forces in the Y and setting those both equal to 0. But now we've learned about moments, okay? So now we're going to set those moments to 0 to kind of complete the picture for what we call the 3 equations of equilibrium. And the 3 equations of equilibrium we want to list right below here. They are sum the forces in the X equals 0, sum the forces in the Y equals 0, and sum the moments about a point, and we'll always identify what that point is, also equal to 0. Our class is called statics. So when we talk about equilibrium, we are in static equilibrium. That means we are not moving. That means everything is in balance, okay? When you take physics, or if you've taken physics, or you might be in physics, there's something called dynamic equilibrium, okay? We are not in dynamic equilibrium. In statics class, we are in static equilibrium. So we are at rest. everything is balanced and some of our forces, some of our moments equal zero. Okay, that's the key here. So now we have a new convention. We've already looked at that in module 4. So we're going to continue to use that new convention where we say everything going to the right and up is positive, as well as all of our moments that are going counterclockwise are also positive. Okay? Also positive. Now, free body diagrams. We're going to be doing more and more free body diagrams here. And up until this point, I think we've been able to reasonably make free body diagrams because most of the items have been given to us. But we're going to find here in Module 5, Chapter 4, that there are going to be some things that when we look at a picture, we've got to actually add some forces for them, okay? So when we do a free body diagram, there are some essential things that we need to make sure that we include, okay? Number 1, okay, all forces, okay? And that's going to be represented as vectors, okay? So that means that if we're showing a force, it has to have a line and an arrowhead because that arrowhead lets us know what direction it is going in, okay? Another thing we need to know are what are any dimensions or locations that we need to be aware of. Because as we know, especially when we're looking at distances between things, they're going to come in handy when we're summing moments, okay? Another item that we're going to have to make sure that we add is going to be the convention. Okay. The convention lets us know as we work down into our equations why we're assigning positive and negative to something. So each one of your problems always needs to start with a convention. Okay. And we always put that right by the free body diagram too. Okay. And then number 4 is going to be any or I should say labels. I'm going to call it labels in general. Okay. Labels and I don't know, I'm going to say magnitudes. So for instance, when we're calling out forces, we want to say, is it force 1, force 2? And if we know its magnitude, we want to make sure that we have the correct value with its units. Okay. So all of kind of the information about that problem in a simplified version is what our free body diagram is going to be. Okay. Now, specifically, this section 4.1 is called equilibrium in 2 dimensions. Okay, so section A here is going to be, let's look at the reactions that we're going to see of forces in 2 dimensions. And all that means is we're only dealing in the X and the Y. We're not dealing in the Z direction. Okay, all right. So if we look at page 160, and I'm gonna pull up that diagram here on page 160. You're going to notice that what they have here, and this is figure 4.1. What they have here is they have a table. And the first column in the table is identifying the support or connection, okay? And it can be, and they're giving us examples of how we might see them in the illustrations, in problems, going forward, or examples that we're going to be doing. So the first one we have here is a roller support, okay? A roller support. Now, a roller support is only going to have one reaction, okay? A roller support is going to have one reaction, and that reaction is going to be perpendicular to the surface that the roller is riding on, all right? We'll be identifying those and putting those in our diagrams. So a roller can look like any one of these items here, and it's going to be one force, and it's always going to be perpendicular to the surface we're riding on. The next one that you see here, and we see them in 2 different portions here. So we have one as a cable, a short cable. A cable, for it to support, it has to be in tension. And it will always support along the line of, in this case, the cable, and it will always pull away from the body. It'll be along that line, okay? So if that line is not horizontal or vertical, as you can imagine, then we're dealing with components, right? Okay, so something to be aware of. So cable, the reaction is going to be along the line of the cable pulling away from the body. If we have a short link, now a short link looks similar, but there's thickness there and it's probably made out of some sort of metal. Okay. So it's going to be along that line of that link, but it can either point towards or away from the body because if you think about a link, it's not going to collapse if you push on it. A cable would collapse if you're pushing on it and it wouldn't be supporting at that point. If it's not in tension, it's not supporting. So that means it's always pulling away from the body. This one can go towards or away from the body, but still along, the direction of that link. Okay. The next one that we have here is going to be a frictionless pin. Okay. We're not going to be dealing with a frictionless pin in a slot like we see here. So I'm going to kind of skip over it, but it would be along the line of action and perpendicular to it. But we won't see any of those in our statics class. The last two, though, are two more that we want to be familiar with. This one is called a frictionless pin. Okay, so we call it a pin reaction or a pin connection. Okay, a pin connection is always going to have, and we're always going to show it in this orientation, two reactions. Okay, it's going to be in an X direction and in a Y direction. Okay, and the reason it is because when we have a physical pin that goes through here, if you look at this pin, this is constraining it from not being able to go back and forth or horizontally or up and down. So that means it's supporting in those two directions as well. Okay. Compared to, very similar to, but compared to a roller allows this to freely move back and forth, but it has to be in contact with the surface to support. So that's why there's one force perpendicular to the surface it's riding on, not, if you would in these cases, horizontally. Okay. So just one for rollers, two for pins. And then the last one that we have here is called a fixed support, or sometimes if it's in terms of a beam, it's called a cantilever beam. You might have heard that before. Okay. So a fixed support has three reactions. An X, and we're going to show it always in this orientation on the right-hand side, an X, a Y, and a moment or a rotation. Okay. So if we look back here, and you'll reference back to this page 160, but in the next section here, it says common supports and their ability to react to applied forces. So pins, there are going to be two reactions, one in the X and one in the Y, always. Okay. So if we have a pin, for instance, at point A, that means that we're going to have an AX and an AY, right? Rollers are going to be one reaction, and it is always going to be perpendicular to the surface that it's riding on. So if that surface is horizontal or vertical, easy. It's going to be horizontal or vertical, opposite, whatever, perpendicular to whatever that surface is. But if the surface is at an angle, it's going to be perpendicular to that angle. So then we're probably dealing with components. Okay, so fun stuff. Okay, so one reaction for a roller. As we turn the page, a frictionless surface. This is like a roller. Okay, it was in that same group. It's going to be one force perpendicular to the surface that it's riding on. A cable, that was this one here, that is one reaction along the line of the cable pulling away from the body, as we had said. And then a rigid link is also one reaction along the line of that link, but it can either be pointing towards or away from the body. A fixed support, okay, a fixed support is going to have three reactions, an X, Y, and a moment. And then a rough surface with friction. So that was in the pin category, rough surface, and that's also going to have two reactions, one for the friction force and one for in contact with the surface. Okay. So again, see page 160. Those are the illustrations that we see here, and we'll pull these back and forth as we do some problems in reinforcement here. Now, as we look at these problems, what we're going to find is on our problems, we're going to see supports that look like rollers or pins, or we're going to have to start identifying rollers and pins. And there's not going to be forces identified for us. And that's where knowing what are the reactions of those supports, we have to fill them in based on, the practice and things that we do. And it says here, most of our problems, you will be solving for unknown forces and reactions at the supports, okay? You'll be solving for unknown forces and reactions at the supports. So a lot of times we know what are the applied loads. So those are the ones like we've been seeing on a beam. We've got 200 pounds going down at 1 foot over from A. We've got the weight of it that's going to be at its geometric center that's going to go down. But now we know that something has to support those either on its ends or along the length of whatever the body is. Well, what's happening there? Okay. And that's where we start categorizing those reactions, those supports. And now what are the forces that we're going to see there? All right. So the process that we're going to go through, not very hard, two steps, really, two main steps is, first of all, assuming that all bodies are in equilibrium. So going forward, that's going to be the condition that we are going to be in. We're going to be summing everything and it's going to always equal 0. Okay. We are going to first draw our free body diagram. That's what FBD means, free body diagram. And what do you think is going to be filled in here? The convention, yes. Free body diagram and convention. So that means that we're going to have all of our forces, add all of your forces of your applied loads, known magnitudes, unknown variables, any dimensions that are out there. And then we're going to add all of the reactions at the support. So we have to be able to look at a diagram or at a picture that they're giving us and be able to pick out, well, there's a support and it's a roller or it's a pin. And then we're going to be identifying that type and then also adding the vectors to represent however many forces would be appropriate for it. Okay. We want to use the equations of equilibrium to solve for any unknown loads and reactions at the supports. So the equations of equilibrium, which we know to be some of the forces in the x equals 0, some of the forces in the y equals 0, and some of our moments equal to 0. Let's list those right here. We'll just list them as long as we're here. Some of the forces equal to 0 in the x direction, some of the forces in the y direction equal 0, and some of the moments around a point are also going to be equal to 0. Okay. Now, when we talk about equations of equilibrium, and I'm going to continue to reinforce this in the examples that we do, this is an equation of equilibrium. Notice that it has an equal sign and it has two sides. So when we identify that we're going to sum our forces in the x equals 0, we first have to start with what I call and refer to all the time as the equation in variable form. This is the equation in variable form. Sum of the forces in the x equals 0. I haven't put anything in there yet. And you just want to basically tell me what you're going to do, and then you're going to add your numbers below. Okay, so that means if I'm summing my forces on this left-hand side, this is going to be summing my forces. And if I'm summing my forces in the x direction, I'm looking at my convention. And if the force is pointing to the left or to the right, is going to give me my positive or negative value. Okay, once I add those all up on this left-hand side, I always have to set it equal to 0 because I continue with an equation of equilibrium. So one of the things that I'm going to be looking for and also demonstrating and pointing out is that you always have to have two sides of an equation. Okay. If you forget to put the 0 in, as you're doing your work and all of a sudden it magically appears at the end, that's points off. Okay. Because that's where we can run into problems with the wrong sign at the end and such, because then if you're not moving correctly from one side to the other to solve for unknowns, you can, you'll get wrong answers. So we want to be sure that we're always remembering our equal to 0. Okay. It might not seem like a big deal, but it actually is. All right. So let's look at our first problem that we're going to look at for our practice problems here. So instead of doing the sample problem that they have kind of in the order here, what I wanted to do was to instead go to our problem section. There were some other ones I wanted to start with before we jump into what they've got going on in the chapter. So the practice problem I want to look at is actually problem 4.2, and this is found on page 174. And what we have here is we have a 2,100-pound tractor. So that's telling us what that tractor weighs. It is used to lift a 900-pound load of gravel right here. They want us to determine the reaction at each of the two rear wheels and front wheels, which are identified as points A and B. Okay. Now you're going to notice that they have this G. This is the center of gravity. That means that this 2,100 pounds is going to be located and concentrated right there going down. Whenever we know the weight of something, that force is always going to be directed down towards the center of the earth, right? It's always going to be down and it's always going to be vertical. Okay. And this is just telling us what's the dimension from point A to where I can concentrate the weight of this tractor. Okay, so we're going to draw a free body diagram here. Now, remember, free body diagrams are simplified versions of, and they usually don't even look like the actual item. Okay, so we're not going to draw a tractor. All right, we're going to draw a simple horizontal line, and it's going to start at A, going to be a horizontal line through B, and then extend to where the force of 900 pounds is coming down. So all we're going to do for this, for drawing our free body diagram, actually, I'm going to add my convention first. I'm going to put it in the upper right-hand corner here because we don't want to forget it. And for this problem, all we are going to do is we're going to draw a horizontal line, okay? The point over on the left-hand side is going to be point A. And then right about, I don't know, here, I'm going to put B, not all the way to the end, but this is going to represent point B. Okay. And then on the very end here, this is going to be that 900 pounds. So I'm just going to kind of put a point there for right now. Now, if we look back at our diagram, we want to put in what we call our applied loads, okay? Our applied loads are going to be the things that we know are there or are shown. So we know the 900 pounds is going to go straight down at the very end. So I'm going to add that right here. Now there's no letter associated with the end. It was just a point, the extension of, okay? So this is going to be 900 pounds, okay? The other point that we know is this G. Okay, and we know that it's 20 inches to the right of A and then 40 to B. So right about here, I'm going to put that 1,200 pounds. And that's the weight of the tractor. And if you wanted to put, G here, that's fine to represent that. Now, additionally, what we're given here is the dimensions, okay? We always want to add, oh, I'm sorry. Go ahead. Oh, was it 21? I'm so sorry. You're right, 2,100. Thank you, Nia, for catching that. 2,100, not 1,200. 2,100 pounds. Yeah, that would affect our final answers, wouldn't it? 2,100 pounds. Thank you. So now what we want to do is we want to also add our dimensions in here, like how far apart are these points? So going back from the diagram, between A and G, it's 20 inches, 40 inches from G to B, and then 50 inches from B to the end. So 20 inches, 40 inches, and 50 inches. Now, as we know, some students will sometimes ask, well, can I extend these forces down below? Yes, you can. Remember the principle of transmissibility, whether I have it on top of the beam or if I'm pulling down below the line or the beam here, it's not a beam because it's a tractor. It'll have the same net effect on the body, in either orientation. So whether you put them on top or the bottom, just sometimes wherever the room is makes sense. Okay. Now A and B, okay? A and B, let's look. A and B for this tractor are doing all the supporting of those loads on top, right? It's supporting the weight, it's supporting the 900 load that we have of gravel in the scoop, right? Or in the bucket. So as we look at A and B, and we think about those reactions that we were talking about earlier, the ones that are on page 160, okay? Are there any that look like they would make sense for the wheels of a tractor? And I'll pull the chat box out if anybody wants to chime in. Oh, shoots. Shoots, I gotta hold on. What was that? The roller. Yeah, we heard roller. Anybody else have any? Yep, roller, right? Looks like that ish, right? Yep, yep. So these are considered rollers. And if we look at rollers, remember a roller is going to be one reaction perpendicular to the surface that our roller is riding on. Okay, perpendicular to that surface our roller is riding on. So we go over here. A, that means we're going to have a force, A, and I'm just putting it down below. Again, you can put it on top of the line or down below. It's going to be going straight up. And I'm going to call this AY just because it's going in the Y direction. Okay. And then B is also a tire or a roller, right? That's going to be a BY. Now, I had them going up, right? If you don't, you may not always know which way they're going. And you might not even know right now, like, are you sure they're both going to go up, Kelly? I don't know. I did the problem already. Yeah, I'm sure. I'm sure. But this is how we think about it. Now, remember our rule of equilibrium. Okay. Our rule of equilibrium. I have to have, if I'm in balance, that means that my total going down has to equal the total going up, right? So chances are these two are going to have a reaction where they have to support the stuff that's coming down. So they have to support going up, the reaction. Okay. But like I said, the direction isn't always obvious. All right. And when it's not obvious, all I want you to do is put a force there, assume a direction, and I'm going to show you how your math will tell you if you did it correctly or not. Okay. So what I'm saying is, I know these are rollers, right? I know these are rollers, but are they going up or down? I'm not exactly sure. That's okay. Pick a direction. All right. And give your best guess first, and your math will let you know if you were okay or not. So don't worry about that, but just put it there, because if you don't put it there, well, now we're not taking it into account, and that's a wrong answer. All right. Okay. So our diagram, three-body diagram, and our convention does it look like it's complete? I think so, right? We've got our reactions identified, one perpendicular to the surfaces. We've got dimensions, we've got labels, we've got units. All right, so I think we're ready to go to step number 2. Use the equations of equilibrium to solve for the unknowns. We have 2 unknowns here. We have 2 unknowns. So I'm just going to start at the top. Sum of the forces in the x equals 0. So I'm going to say sum of the forces in the x equals 0. Do I have any forces in the x direction? No. So there's nothing to do there. So you're going to notice I have some of the forces in the y, right? So I'm just going to leave it at that, because there's nothing to solve for. There's nothing to add in here. So if I had some horizontal forces here, I would add those on the left-hand side, but I don't. So we're just not going to continue on. So my second equation of equilibrium is sum of the forces in the y equals 0. Sum of the forces in the y equals 0. Here I've got forces, right, in the y direction. So I'm going to start on the left-hand side here, and I'm going to work all the way to the end to the right, and I'm going to use my convention. So now I'm in force mode. So I am only looking at the y direction. Is this force going up or down? Okay. If it's going up, it's going to be positive. If it's going down, it's going to be negative. So I assumed AY was going up. So I'm going to put a positive AY. Okay. So remember, you have to tell me you're going to sum your forces in the y equals 0. And then down below, we're going to do that. So I'm on my left-hand side of my equation. So AY positive. My next force is 2100. It's going down. That's going to be a negative 2100. And don't forget to add your units. Put your units in all phases of the problem. Then I'm going to move to the right. That's going to be BY. It's going up. I assumed up. So it's going to be plus BY. And then all the way over, I'm going to have a minus 900 pounds. Don't forget your units. Now, this is the left-hand side of my equation. This was the sum of the forces in the y. I need to set that equal to 0. If you don't do this, points off, I'm sorry. All right. So now I have an equation. I have two sides and I have an equal sign. So now I want to combine what I can and then see what I have left over. So I can combine the 2,100 and the 900, right? And that would be 3,000 pounds, right? So I would say AY plus BY minus 3,000 pounds is equal to 0. I can move my 3,000 to the other side, so I can say AY plus BY is equal to 3,000 pounds. But that's as far as I can go, right? Because I have two unknowns, right? So what we're going to do is we're going to leave a little space here because I'll probably be able to kind of fill something in a little bit. But I have one more equation of equilibrium, don't I? I used my sum of the forces in the x, and there weren't any forces in the x, so I was kind of like I didn't need to use it. But some of the forces in the y got us some progress, but we weren't able to solve for our two unknowns, which are AY and BY. What's my third equation of equilibrium that I could use? Some of the moments around a point are going to equal to 0. So this is where you strategically place your point, okay? If I put my finger on A, do you see how AY won't be part of my equation? Because it's going to push on the point, it's not going to rotate, but BY will be part of it. So if I sum around A, if I sum around one of the points where one of my unknowns is, I'm taking that one out of, if you would, the equation. So I end up with only one unknown. If I sum around the 900 over here, I'm going to have an unknown at A and an unknown at B, and I'm in the same boat as I was right here. So summing your moments and then thinking strategically, which one of these do I want to take out, if you would, will then leave the other one to be solved for, and then I can do the substitution back. So that's what we're going to do. I'm going to sum my moment around A. So leave a little bit of room here. Tell me you're going to sum your moment around point A equal to 0. This is an equation of equilibrium, two sides, equal sign. Then I'm going to put my finger up on A. Y will not be included because it's pushing and the distance would be 0. So it wouldn't be there. But 2,100 is causing a rotation. So I'm going to have 2,100 pounds times 20 inches, and it is rotating clockwise. So down here, I'm going to be a negative out front, 2,100 pounds times 20 inches. Inside of here, I always put the symbols because it's shorter to write. But then as we, do some things and get to the end, then I use the LB and IN. So that's my first moment. Then I'm going to put my finger back up on A and I'm going to pull in the direction that I assumed for BY. Okay. So BY is the force. Its perpendicular distance is going to be 60 inches. And it is rotating counterclockwise. So that's going to be a positive out front, BY times 60 inches. Then I'm going to go back up. I've got one more force. I've got the 900. The 900 is going to cause a rotation. So it's going to be 900 times perpendicular distance. It looks like that's 110 inches. Okay. And then it is going to rotate clockwise. So negative out front, start your parentheses, 900 pounds times 110 inches. Now, if I look up here about A, those are the only three forces that are causing rotation. So that means I've got all of my moments accounted for. So I summed my moments around A on the left-hand side here. I have to set it equal to 0. Okay. So now you'll notice that as we look here, our only unknown is BY, right? Only unknown is BY. So you want to go ahead now and you want to combine and solve for BY and see what you get. See what you get. I'll kind of do it on the side here and you can compare, but I encourage you to combine So you should end up with a negative 140,000 pound-inches when you combine these two over here, this first one and this last one. And then it's going to be plus By times 60 inches is equal to 0. And then you're going to take the 104,000, you're going to move it to the other side. It becomes positive pound-inches. And then now my By times 60 inches is left over, and I'm going to divide both sides by 60 inches. The inches cancel. Okay. And my By, when I take 140,000 divided by 60, should be 2350 pounds. Okay. Or LB, whatever you want to do. I kind of alternate. I don't know why I alternate back and forth. I don't know why, but I do. No, you didn't get the same answer. Chris is like he's.
I'm getting up to 40.
Oh, it was. I'm so sorry. See, I worked these. I'm glancing over and I missed that. Yep. I have it written as 141. Yep, I do. Negative 141,000. So sorry. And then divided by 60. I work them out ahead of time so I don't have to punch the calculator as I go along. And I have it. It's right. Yep. It's right on my paper. I just didn't translate it correctly. So now that I have By is equal to 2350 pounds, I can go back up to my sum of my forces in the Y direction equal to 0, and I can substitute my By back in here. Okay. So then I can say Ay plus 2350 pounds is equal to 3,000. And if we move that over to the other side, so this would be minus 2350. My Ay is going to be equal to 650 pounds. Okay. Now, everybody get the same answer? Now, I want to tell you something really important. Okay. So if you're not listening, come back to me right now. You'll notice here for By and for Ay, we ended up with positive answers. Okay. Now, I'm going to tell you, we assumed a direction of up here. All right. We assumed a direction of up. In our problem here, that's the math, that's the sign that we used. And when we got to the very end, if we end up with a positive value, that does not mean the force is going up. It means that the direction we assumed was correct. So even if I had a problem where maybe my reaction I assumed was going down, but if I end up with a positive value as my magnitude, that means whatever direction I assumed was correct. So I happen to assume up here, so getting positive values for A and Y means you indeed were correct in that direction that you assigned. If I would have ended up with a negative for either one or both of these, I never leave an answer as negative because that tells me you didn't pick the right direction, whatever it was, up, down, left, or right. And that means you have to change the direction up here and make it correct. And there'll be a couple examples as we go through here that I already have figured out that we're going to definitely do that. All right. But I want to that's a very important point. Your final answer being positive confirms the direction you assumed. Okay. Yes, these forces were assumed up, but they're positive as their final answer because I assumed the correct direction. Okay. Again, I will continue to reinforce that as we go through. So that was how I knew I'm okay on my direction because I have a positive final answer. Okay. So that's where I want you to know. If you're not sure which way those forces should go, just put the force in. And then you will know here if you were okay or not. Okay. So questions on that first problem. All right. Make sure you have all these elements that we've been talking through. Let's turn the page and do another problem. Okay. The next problem we're going to do is on that very same page, and it is problem 4.3. Problem 4.3. Okay. So problem 4.3, we have a gardener uses a 60 Newton wheelbarrow. So whenever we identify in a problem 60 Newton wheelbarrow, that's telling us what the weight of that item is, okay? 60 Newton wheelbarrow to transport a 250 Newton bag. So that's the load that she has in the wheelbarrow here. What force must she exert on each one of the handles? Okay, so you're going to notice that she's holding it up at the handles there. Well, what is the force that she has to exert to keep that in that position? Okay, so what we have here is we've got a point A, that's going to be the front part of the wheelbarrow, the wheel of the wheelbarrow. We've got the 60 newtons coming down, so they showed us that. But if, let's say, there was a G here like it was on the last one, we would use that 60 newtons and we would show it going down like they see here. Okay, but they've positioned that for us and they gave us the dimension between. The 250 newtons going down for the bag of fertilizer. And then over here, this last dimension is going to where she's holding the handles on that wheelbarrow. Okay, we are going to draw our free body diagram as a straight line again, starting at A and going all the way to her hands, if you would. Okay. Now remember, per the principle of transmissibility, whether the force is up here or down here, it's going to be along its line of action. So we can show this just as a straight line. Okay. So step number 1 is going to be free body diagram and convention. So I'm going to put my convention up here. And it's going to be the full convention with the positive moment going counterclockwise. And my free body diagram is going to be, as I stated, a simple horizontal line with point A here. And I'm going to call her hands point B. Okay. Now, we're going to show that 60 newtons. That's the weight of the wheelbarrow at its center of gravity. And this is 60 newtons going down. Then we've got the 250 newtons. And that's going down. And then I want to put the distances that they give us in between here. So this is 0.15 meters between A and the 60, another 0.15 meters between the 60 and the 250, and then the 0.7 meters to B. Now, to hold this up, we have 2 supports, and we want to find those reactions at those supports. Support A is going to be the wheel in the front again, okay? So as you can imagine, it's going to be kind of like the last one, right? It's a wheel. It's probably going to be like a roller, like we did. And then we have our hands that are, lifting up, right? That's our other support. Now, this one's not as obvious, but the way that her arms are positioned, she would be lifting straight up vertically. So we're going to just simulate that as a vertical force going up, okay? So at B here, we're going to show this as BY. Again, Y just because it's going up. And then I'm going to show AY from the bottom up just because, to me, the wheel is on the bottom, it's hitting the ground, but you could put it going on the top side too. Okay. So any questions right now about the free body diagram? Right? So one force at each one of the supports, and they're both vertical, they're both pointing up at this time. Okay. And we'll see if we're right or not. All right. So the next thing we're going to do is, using the equations of equilibrium, we're going to solve for our unknowns. Our unknowns are just 2 of them, AY and AB. Okay. Now, this time you're going to notice that, yes, we have 3 equations of equilibrium, but which one won't we use? Some of the forces in the X, right? Some of the forces in the X equals 0 because there are no forces in the X direction. So we're not even going to worry about that one. We're not going to write it this time at all. So which one do we want to use next? Sum of the forces in the y. Let's write our sum of the forces in the y equals 0 equation and see what that looks like. So we're going to sum our forces in the y direction equal to 0. You have to tell me you're doing this. Don't just run in and start writing numbers down. I don't know what you're doing. You got to tell me what you're doing so I can follow it. So sum of the forces in the y equals 0. So now I'm going to look starting left to right, and I'm going to write each one of my forces. If they're going up, I'm going to give them positive. If they're going down, I'm going to be negative. So go ahead and write the left-hand side of this equation. I'll give you a chance to do that. So when I'm sum of the forces in the y mode, I am only looking at the vertical pointing up or pointing down. So AY pointing up, so that's going to be a positive AY. 60 newtons pointing down, minus 60 newtons, minus 250 newtons, and then plus BY. So again, that is purely, am I up or am I down? And then I'm going to set this equal to 0. Equation of equilibrium and equal sign, two sides. So now I'm going to combine what I can, and I can combine the 60 and the 250 newtons. And I'm going to have an AY plus BY minus 310. Is that right? Yeah, I think so. Newtons is equal to 0. And then if I move my 310 to the other side, now I've got two unknowns, right? I can't go any further. So I'm going to leave a little space here because just like the last one, I'm going to be able to come back and kind of fill in. But what is the next thing that I'm going to consider? I'm going to consider the moments, right? Yeah. And I'm going to go back up here and I'm going to decide where I'm going to sum my moments around. Am I going to go around A? Am I going to go around the 60? Am I going to go around the 250? Am I going to go around B? Which two would I want to consider? A or B, right? I can consider A or B as where I'm going to sum my moments around. Where do we want to sum our moments around? Why don't we do B once? Why don't we do B once? We've always done A, right? Did you do A? Did you already write it out? That's boring. Let's mix it up a little bit. Left to right. I know. We're gonna go outside the box. I'm gonna go around B. Did anybody already some moments around A? Like I'm speedy, I'm already okay, Jaden, leave it. And then you're gonna see, do I get the same answer? Because what I want to show you is whether you go around A or you go around B, you're still gonna get the same answer, in the end. All right. So it really doesn't matter. It's gonna be whatever you choose to do. So I'm going to go around B this time. We're going to mix it up. So that means I'm going to leave a little space here. I'm going to go down here. I'm going to sum my moment around point B equal to 0. Okay, equal to 0. My same convention applies. That doesn't change. But I'm going to work this way. So I'm going to go 250 newtons. That is going to rotate counterclockwise. So that means I'm going to have a positive out front. 250 newtons is my force, times my perpendicular distance from B is 0.7 meters. Okay. Then I'm going to go back up here, B, pull in the direction of 60. 60 newtons is my force, and this time it's going to be 0.7 plus 0.15, so 0.85 meters is my distance, and it's rotating counterclockwise. So that's going to be a positive out front, 60 newtons times 0.85 meters. Okay. And then my last force, which is my unknown, is going to be AY. It's going to go clockwise, and AY is going to be, looks like 1 meter away from B. So minus, and then it's going to be AY times 1 meter. And then those are all the forces, so I have to set this equal to 0. So the left-hand side is the sum of the moments around B, and the right-hand side is equal to 0. All right? So now, yeah, I've got to, I didn't sum my moments around, I did my moments around A on my paper too. So now I got to calculate this. 250 times 0.7. So that's going to be 175 Newton meters plus 51 Newton meters minus AY times 1 meter is equal to 0. Okay. So now what I'm going to do is I'm going to combine these two. It's going to be 226 together, and I'm going to move them to the other side. So I'm going to have a negative AY times 1 meter is equal to a negative 226 Newton meters. See what I did there? Okay. Negatives on both sides, they both become positive. Okay. And then I'm going to divide both sides by 1 meter. This one's kind of easy, right? And my AY is going to equal 226 newtons. Okay. Box around. Now that I have AY and I know it's 229 and I got a positive number, so that means that the direction going up was confirmed to be the correct direction. Okay. Now I can take this and I can put it up in this equation here. So that's what I'm going to do. I'm going to say, all right, my AY is 226 newtons plus BY is equal to 310 newtons. Okay. So if I take and I put the 226 on the other side, my BY should be 84 newtons, right? And it's a positive value. So the direction of BY was assumed correctly. Now, Jaden, did you get 84 and 226? Oh, Greg did it too? Yes. Yeah. So whether you do it, sum your moments around A or sum your moments around B, you get the very same answer. Did you also get positive values for your variables or for your magnitudes? Yes. Perfect. So it works both ways. All right. Any questions? Chris?
So if we did get a negative,
Yeah.
They'd get out your do it, or
Yeah, Chris has, like, what if we get a negative value? It is not, you don't have to redo everything, but it's a two-part problem. First of all, you make this number positive. Okay, so let's say the 84, let's say I went through and I thought, oh, BY is going to go down. Okay, and when I got to my answer here for BY, it became negative. All right. So first thing I do is I make it positive because you never leave a final answer as a negative value. Okay, first thing. So you're going to make that positive. And then the second part of that is I am just going to change the direction, the exact opposite of whatever I chose. You do not need to redo the math. Okay, but I'll know if and there's no shame in getting a negative value as long as you fix it. That's it. All right. We never have a final answer as a negative value. You don't leave it. Then that's your clue that I don't have the right direction. I just need to change that direction. Okay. So I always look, what is your final direction, and making sure that you have a positive number here. Okay. And I think I have at least 2 examples where we assume a wrong direction on purpose so that we can go through that process. Okay. So we'll see that play out. Other questions here? All right. Okay. All right. Turn the page. Okay. Now we're going to go back to sample problem 4-1. I believe this will be our last problem for the evening. Okay. And that'll give us a good positioning for the next time that we're together. So now what we're going to do is we're going to kind of back up in the chapter. I wasn't crazy. This was their first example that they wanted us to go over. And I actually was like, that's kind of jumping in. So that's why we did a couple, I'm gonna say beginner problems. And now we're gonna look at this. Okay. I just didn't want to look at this for your first one. I think that's kind of intimidating, but now we've got a couple problems under our belt and I think we're ready to look at this. So sample problem 4-1. So it says here that we have a fixed crane. So it's over here are the supports at A and B. It has a mass of 1,000 kilograms. We'll deal with that in a little bit. And it's used to lift a 2,400 kilogram crate. It is held in place by a pin at A and a rocker slash roller at B. Okay. The center of gravity of the crane is located at G. Determine the components of the reactions at A and B. Okay, we're going to solve for the reactions at A and B. That's all that means. They're using the word components. Don't worry about that because we've got vertical things. We're going to be X's and Y's anyway. Okay, so this is what we got. So free body diagram and convention first. All right, so convention up here. Now, simplified free body diagram, okay? How we're going to draw this. I just want to look at my, so here's my free body diagram. And I just want to look at my size here so that I can make sure I have enough room and then I get everything in. This down here is going to be my point B. And up here is going to be my A. Okay. And then we're going to just draw a horizontal line going out to that load out here. And I don't think they're calling it any letters, but G is along the way here. Okay. So this distance between these two is 0.15 meters between A and B. And A and B are our supports. That's where that pin and that rocker slash roller are. Okay. Our center of gravity is here, and they give us a dimension of 2 meters. And then from G to the end point, which doesn't have a letter assigned, is 4 meters. Okay. Now, in our problem, they are telling us that they're giving us the mass of the crane and the mass of the crate. All right. These are not forces. These are the mass. So we need to convert that from kilograms to newtons. And to do that, we want to find the weight, not the mass. So we're going to call this weight. I always call it WT, and we're just going to call it 1 for the center of gravity. Yes. Did I? Oh my gosh, thank you. Nia, you're my mistake finder. 1.5 meters, not 0.15 was in the last problem, wasn't it?
Yeah.
I said it right. Oh, see, Chris, you knew it. Tell me, wait, Kelly. Talking and writing aren't as easy as it may look. You know that? Okay. All right. I think we're 1.5, not 0.15. Okay, my weight here is going to be the mass times gravity. Okay. Now the mass is given to us as 1,000 kilograms. Okay, so that's going to be 1,000 kilograms times gravity. Now, since we're in the metric system, gravity is 9.81 meters per second squared. Okay. A kilogram times meters per second squared is a newton. Okay. So when I multiply these two together, my weight number 1 is going to be 9,810 newtons. Okay. In your physics class, if you've taken it yet, or along the way, you may have run across that. If you haven't, that's okay. I'm giving it to you. So whenever we see something in kilograms, we know, oh, that's mass. We just have to multiply that by gravity to get what it is in newtons. Okay. So that is going to be the force then that we show going down at G. Okay. We know this to be 9,810 newtons. Do not put 1,000 kilograms because we are calculating forces, not masses. Okay. So now we want to know what is the force that we're going to show out here at the end, and that's going to be our weight number 2. So WT2 is also mass times gravity. This time our mass was 2,400 kilograms. So we're going to multiply that by the same 9.81 meters per second squared. So our weight 2 looks like it's 23,544 newtons. So this is 23,544 newtons. Okay. You guys get those same numbers if you're punching them in? Okay. All right. So those are what we would call our applied loads, the weight and that crate out on the end. Okay. And whenever we have weights, they are always going to be forces that will be directed down towards the center of the earth. So they're always going to be vertical, pointing down. Okay. Now we've got 2 supports, and they already told us there was a pin at A and there was a roller slash rocker at B. Okay. So A, we go back to page 260. This is the frictionless pin. Okay, even though it didn't say frictionless pin, kind of assuming that it's frictionless. 2 reactions, okay, X and a Y. So over here, we're going to show an AX and an AY, right? So we're going to call this AX, and I'm just showing it going to the right just because, all right? I'm just showing it going to the right. And then I'm going to show at A also the Y direction, AY, because remember, we're going to be 2 reactions for a pin, horizontal and vertical. Out of the way here. So AX, AY. So 2 reactions at A. And then B, okay? Where B is positioned, you're going to notice that the wall that it rides on is vertical. So that means it's going to be one force perpendicular to the surface it's riding on. Okay, so that means it's a horizontal or a BX. So I'm just going to show it going to the right as well. I don't know which way it's supposed to go. We will find out. We're not afraid of it. You don't have to try to overthink this. Okay, don't try to get all these in the perfect place, because we really don't. I mean, we see there's reactions, we see there's supports, but now we've just got to put a force there and like hope for the best. Okay. All right. So now we want to use our equations of equilibrium. Step number 2 is going to be our equations of equilibrium to solve for our unknown quantities, which are AX, AY, and BX. Okay, so where do we want to start? Sum of the forces in the X? Sure, let's sum our forces in the X equal to 0. So we're going to say sum of the forces in the X equal 0. So if we look, oh, this time we have 2 forces in the X. We have a positive AX and a positive BX. Okay. So we're going to say AX plus, so if we want to put the positive out front, you can do that, plus BX equal to 0. There's only those 2 forces, so we set them equal to 0. Unfortunately, we don't know either one, but we're fine. We'll probably come back to that, right? So we'll just leave this here. What do we want to do next? Sure, we could sum the forces in the Y, and we can see how we do. Now I'm going to show that one over on the right here. I'm just going to go over here. I've got some space. So sum my forces in the Y equals 0. Remember, I'm always telling myself, or Kelly, if you're writing it for me, what you're going to do. So you have to tell me sum the forces in the y equals 0 and then do it. Sum the forces in the x equals 0 and then do it. I don't want to all of a sudden see ax plus bx is equal to 0. What were you doing? Okay. Let me know. Equation in variable form first. So looking at the y, I've got a positive y, right? Positive ay. I've got a negative 9,810 newtons, and I've got a negative 23,544 newtons. Am I ready to add those together and combine them? Nope, I am not. What am I missing on that line? Equal to 0. I cannot emphasize that enough. Equal to 0. All right, now I have an equation, right? So I want to combine these two and I want to solve for AY, okay? So I'm going to have AY minus 33,354 newtons is equal to 0. I'm going to move that to the other side. So that's what AY is equal to. Now, my AY ended up as a positive value. That means I assumed the correct direction. And it kind of makes sense. If we look here, not looking at the x's, look at my y directions. I've got two forces going down. The only thing that would balance it is if AY would go up, right? It has to. It has to, right? So, and indeed it does. So sometimes they're obvious, right? When we do it. But again, this just confirms, yep, you were right on that direction. So I can put a box around it. Now, I still have AX and BX unknown, but I have one more equation of equilibrium, right? I've got sum of the moments around a point equal to 0. What is one of the 2 points that I would consider for summing moments around? A or B. Right. I could go around A or B, knowing that whichever one I do, one isn't better than the other. Okay. A or B, I will get the very same answer. All right. So if you're comparing notes, let's say with a classmate and they did it around different one, it isn't better one way or the other, as long as in the end you end up with the same, answers, if you're comparing. So yeah, we're going to sum our moment around A or B because those are where the unknowns are. We want to get rid of one of the unknowns, right? So we can solve for the other one. So which one do we want to go around? Greg jumped out. He said A. We're going around A. Sure. Let's go around A. All right. So I'm going to sum my moments around A equal to 0. Okay. Sum my moments around A. So tell me what you're going to do. That's what this is. Put my finger on A. That means AX is out of the equation and so is AY, right? They're going through the point. But BX is going to cause rotation, right? And it's going to rotate counterclockwise, and it is offset perpendicular distance from A of 1.5 meters. So I'm going to have a negative BX, no, I'm sorry, positive BX out front because it's going counterclockwise. Positive BX minus, or I'm sorry, times, what am I doing here? Times 1.5 meter. This might be my clue that this is the last example I should do tonight, right? I think so. I think for all of our sakes. Then my next force is going to be the 9,810 newtons times perpendicular distance, 2 meters. And that is going to go in a clockwise direction. So that'll be a minus out front. And I've got 9,810 newtons times 2 meters. Make sure you put your units in. And then I'm going to, one more, 23,544 also causes rotation going clockwise times perpendicular distance is 6 meters. So minus 23,544 newtons times 6 meters. This is the sum of my moments on the left-hand side about A. I'm going to set that equal to 0. So I complete my equation here. And now as I look, my only unknown is bx. Go ahead and solve for bx. You should get 107,256 newtons. Okay. For bx. It ended up a positive value, so that means the direction that we assumed going to the right for bx was the correct direction. Yes, it was positive, but this positive final answer just means the direction is confirmed. Okay. Now we can take this bx and we can put it back up into our sum of the forces in the x equation where we had ax plus bx equal to 0. So we're going to take that 107 and we're going to 107, 256, and we're going to put it up here. So we've got ax plus 107, 256 newtons is equal to 0, right? Then we're going to move that to the other side. Zoom in here, move that to the other side. I got a little room here. My AX is going to be equal to a negative 107, 256 newtons. There it is. The answer is not wrong. The magnitude is correct. All it means is, remember how we thought that was positive up there, or we assumed a positive direction of AX? All it means is, that wasn't right. It's not going to go to the right. It's supposed to go then the exact opposite. It's going to go to the left. So two-part correction here. We're going to make this positive because we never leave any of our final answers as negative values, ever. Okay, so we're going to put our box around this. This becomes a positive 107. And then we're going to go right up here and we're going to erase the vector arrowhead that was going to the right, and we're going to change it to go to the left. I look at your diagrams. I make sure that your final answers are also going in the correct direction. Okay, so you have to correct it up here and down here. All right, and it does make sense. If our bx is going to the right, then something has to equal it out. The ax has to go to the left. So any questions on that problem? That's a good one. It had ax, it had x's and y's and moments, negatives and making them positive. So good. Right. So that is where we are going to, stop for the evening. All right. But before I kind of let you loose, if there is anybody that is like, we're not going to be meeting, for another 2 days, I would really like to start on this homework. Is there stuff that I can work on? And there indeed would be. Oh, does it matter if the bx was negative over ax? What do you mean? Oh, you mean if you had this going to the left to start off with, Ava, and that was going to the right? I don't know what you mean. If you had them going in the same direction I did, bx would be positive and your ax would have been negative, and then we have to change the ax direction. Okay. So, all right. And if you are getting a negative answer here for BX, that means your math in here somewhere is not correct. Okay. All right. I can also talk to you about it on our lab time. Okay. All right. Okay, so let's take a peek at what you have for application problems that you could get started on. So if I look here in Module 5, the application problems that you have, these start on page 174. Okay, so if I go underneath here, I just want to write down 1, 7, 10, 13. So let me see. We'll see how far you can go. So number 1, okay, you'll notice that you have a set of forces that are acting on a beam or a rod. They are supported at A and at B, okay? It looks here like B is a cable and A is a pin. You could do this problem and then just make sure that you represent the cable as a force going down away from the body. The body is the rod or the beam here, okay? And this would be pulling away from the body in the direction of that cable, and it would be one force going down. So you would just show that at B. C is not part of the equation because that's just connecting the cable to point B, okay? So that would be one that you could start working on. The next one that you have assigned is problem number 4-7. I wouldn't do 4-7. I would wait on that one. So you can skip over 4-7. I would wait on 4-10. I would wait on 4-11. So yeah, the first problem you're good for. And we'll probably do some setting up of some of those problems as well as we go along so that you can make progress. So yeah. So I think we got a chunk in our guided notes done. And then the next time we get together, we will continue on, and then we'll also set up some homework problems so that you can make progress on that as well. Okay. So I am going to stop the recording.